everyone to the Science and Data track at PyCon. We expect this room to get pretty full today, so if you could move inwards towards the edge of the, so people can actually come and grab a seat and not climb over you, that would be great, thank you. If you're at the back looking for seats, we've got nearly a whole row free at the front still. Cool, thank you. So we've got a great day planned today. We've got 10 different speakers throughout the day. And so first up, we have Sam Hames. He's a software developer at QUT's Digital Observatory. He works with Python at the intersection of the web, data, and analytics. He started a PhD and he might finish it one day. But he's talking about why you don't always need NumPy. So a bit controversial maybe, but looking forward to it. Thank you, Sam.
I hope this isn't controversial. I was working very, very hard to make sure it wasn't controversial. Little suggestions, little things, little changes. So yeah, the talk. You don't always need NumPy or SciPy or TensorFlow or Pandas or all of the other very, very exciting things that are happening in the numerical Python community. Every time I look up something, there's a link to some other package I've never seen before, and I'm like, ooh, that looks cool. What does this do? And then I'm looking at the XArray docs and wondering, maybe I should refactor some stuff. And then 3 hours are gone. This talk is also a bit of a reflection for me because I first used Python 12 years ago now. I was in a university course. The course was about numerical simulation. So my entry to Python was numerical Python. It was solving ordinary differential equations and partial differential equations in Python. That's where I started Python. Done a lot of other things since then, and I still use numerical stuff within Python. But this talk has been has ended up being a bit of a reflection on that time and some of the things I've learned. So I want to start by stating two things, which I hope are not controversial. Or the first one is an approximation. So the first is that NumPy, when I say NumPy, I'm going to say NumPy and numerical Python ecosystem interchangeably, which isn't really accurate, but for the purposes of this talk, just imagine they're the same. The second thing is that numerical Python is a subset of Python. The Python is not one community, it's many communities, and they tend to overlap. There's lots of stuff going on. So one of the things we should remember is that numerical Python, the whole world is not numerical Python. There's other things going on in Python too. So I think when you're working on numerical computation and stuff, it's very, very easy to get stuck where your whole world is a single equation. It's the core thing at the middle of your problem. It's the machine learning algorithm you're working on. It's the ordinary differential equation you're solving. This is a little bit myopic. It's very, very easy to end up getting stuck just in that part of the problem, forgetting that you actually need to do a whole bunch of other stuff too. Like, you've got to load data from disk at some point. You've probably got some config files somewhere. You might have different experimental settings. You might need to do a whole bunch of other stuff besides that. And then once you've done all the numerical stuff, you probably have to make a chart or a graph, or you need to write the results to a database or spit out a file to give to somebody else, or a spreadsheet for somebody else. So this isn't the whole world. This is the fun part though. Even if you're lucky and you just get to worry about the numbers, eventually somebody comes to you and forces you out of that domain. Maybe you've built something useful and somebody says, well, can we have a web API around that? Or maybe this time series prediction stuff is really cool. Let's build an interactive JavaScript visualization and run it daily and give it to somebody important to click on things. When you hit a situation like this, suddenly you've got more than the numerical domain to worry about. So when we're writing numerical Python, we need to remember that the rest of Python exists. The rest of the world exists. The rest of the problem also exists. And it's when we hit these other problem domains that we end up with a bit of friction. I mean, it could be as simple as you're used to working with Conda, but the web service you need to integrate with, all of their deployment pipeline uses pip, and suddenly you have to care about the differences between pip and Conda. The numerical Python stack tends to be very, very complicated. The packaging ecosystem has come a very, very long way, and it tends to be a lot smoother now than it used to be. But the complexity is still there. There's still new ways for things to break. Lots of things, weird things can happen. And on top of all of that, numerical Python is a different idiom to other types of Python. I remember the first time I was at a job, at my last job, I was working with some very experienced developers who tend to focus on web problems. I ported an algorithm that was plain old Python to NumPy, so arrays instead of dictionaries and things like that. I thought it was perfectly reasonable idiomatic NumPy or numerical Python. I got some funny looks because it was different. It wasn't what they were used to. Like numerical Python tends to be flat, where like it's a different shape in the editor. You look at it and you go, this is not what I'm used to. I think a more fundamental problem is that the practical part of running computational stuff is hard, so we spend a lot of time trying to squeeze our problem domains to fit what we can actually do with our machine. A lot of numerical work is, well, how do I actually represent this as an array? What does this array mean? So when you're working in the numerical Python land, you do have this, you've got this conceptual stuff on top as well as all of the practical differences between different parts of Python. For example, so this is in text analytics applications, it's very common to use a bag of words representation. So if we have a document which is a single phrase, the cat sat on the mat, a bag of words representation is we count the number of times each word occurs in the document, and we represent those counts. So we could do this in base Python as a dictionary. So the occurs twice, cat occurs once, and so on. If we try and represent this as an array, we end up with a layer of indirection. So in the array, we have a convention that the 0th column represents the word the first column represents the word cat, the second column represents the word sat, and so on. So we need to maintain a lookup table between our numerical representation of the problem and our actual problem domain. So in this case, like, I'm not going to care that column 673 is something meaningful in this data set. I want to know what it actually means in terms of the documents that I'm studying. So given that, I'm going to make 5 small suggestions. I'm going to state up front that the keyword is you don't always need NumPy. You can want it. There are some very good reasons to use it, and there are lots of problems where it would be ridiculous not to use it. But NumPy isn't everything, so I'm going to make these suggestions in the context that maybe they'll help you make things a little bit easier for yourself. They'll make your work a little bit faster, a little bit easier to explain to other people, a little bit easier to work across domains. And of course, like any suggestion, you should take them with a grain of salt, pay attention to your particular context, your particular team, your particular problem. So the very first suggestion I'm going to make is remember Python's inbuilt data structures. These are really, really good. They're not necessarily the best if your domain is numbers, but for everything else, they are very, very good. And they're very well optimized. They're the foundation of everything going on in Python. So if something is, it's very unlikely that something is going to be broken in these. I'm just going to refresh your memory. I like reminders of the basic things because I always forget. I forget so much stuff that I keep having to look up, and then somebody reminds me, and then I look at code I wrote 4 years ago and realize I've already actually done it, I'd just forgotten. So a list in Python. The example list in this case has the numbers 1, 2, 3 in order. Those are base Python integers, not NumPy integers. There's a difference, which I'm not going to go into. Lists have the property that it's really easy to put stuff on the end of them and take stuff off the end of them. So if you're accumulating something over time, like a series of results, this is a faster way this is a way to do it. If you need to do anything else with lists, like check membership, then it's going to be, the time will be proportional to the size of the list. So if your problem domain is pure numbers, you probably don't want to use a list. But lists in Python are general purpose, and they're fast when you're considering that they deal with Python objects. You can have a list of whatever Python objects you like. The second one is sets. Like mathematical sets, but they're holding Python objects. So in the example set here has the same numbers as in the previous example list. Adding, deleting, and checking membership of a set is all very fast in Python on average. There's a lot hidden in that on average. We're not going to go into that. One of the really nice things about Python sets is that because they can hold arbitrary Python objects, almost all Python objects, there's a thing I'll talk about in a minute, but they also have a very natural expression of set operations, which as far as I'm aware is actually, you can do all of these things quickly in NumPy, but it's not as nice as, well, this is a set, it has this behavior, this conceptual thing. An array of numbers is, you can pretend it's a set, but it's not a set. Dictionaries have very similar properties as sets. Adding, deleting, and checking membership are really fast, but you can also have a payload value for every key in there. And you can iterate through items, keys, and values different, whatever you need to do for your particular problem. The last one I'm going to mention is tuples. So the only thing you can't put mutable objects, or I'm probably going to get this wrong, ask the core Python developers the details. The things you put in sets and dictionaries need to be hashable. Lists are not hashable because they can change. So if you need to put something like metadata or other things, you need to use a tuple. Tuples are immutable, they're fixed size, they don't take up a lot of space, but you can't modify them as easily. Tuples work really well for things like metadata descriptions. So if you've got some combination of experimental conditions, a good descriptor of them might be a tuple of all of the bits and pieces of that experimental condition. And I mention them because you can't have a set of lists, but you can have a set of tuples. Or you can have the keys of your dictionary being tuples, which is very handy. So beyond the basic Python data structures, don't forget you can glue them together in moderation. One advantage of this is that the semantics of combining things is a lot easier for people to understand because they already know, well, I know how a set works. So if I've got a set of these other objects, that's less thinking. I already know what this thing does. Feel free to nest or combine things in ways that make sense for your particular problem. This gets even better when you consider the fancier data structures that are built into the standard library. So if you haven't ever come across default Dixon counters before, they are great. They save a lot of time. There are a lot of things you don't have to think about anymore. You just go, this is a default dict of lists. And then you don't need to worry about whether the key is already in the dictionary or whether appending is going to fail or all those other things. You can just make it happen. It simplifies your code a lot. This makes composition a lot easier, and you're still using standard library and standard data structures. So most other programmers are going to at least have some understanding of what's going on. I'm also going to point out two things that you may not have come across before in the standard library. There is a priority queue implementation in the form of heap queue. It keeps your priority queue in a list. I mention this one in particular because a lot of algorithmic optimization relies on some kind of sorted or priority queue being built as you go along to make things go faster. Like lots of algorithms that go from n squared to n log n use some kind of queue like that, or heap. The other thing is the bisect module, which is standard bisection search, but it's in the standard library. So you can do lots of interesting things like with that if you're working with data that is sorted or is required to remain sorted. The last one I want to, in terms of pure Python, the last one I want to mention is generators and streaming. So in numerical Python land, I think there's this kind of implicit assumption that everything you're going to do is going to fit in memory. You don't have to worry about memory. Machines, your problem, you've just got enough RAM. You're not going to run out. But eventually you do run out. Like this is a cheap laptop. It has 16 gig of RAM, and I kind of regret not going up from there, just because. Another side effect of this assumption that everything is in memory is that just everybody just gets used to work of going, oh, okay, it's a data frame. I'm sorry, it's a CSV file. I'm just going to read it into a pandas data frame. It doesn't matter what you're actually going to do with it afterwards. Like, if you're doing aggregations and group bys and sorting and time series, yeah, that makes sense. But if you're then just going to iterate through all the rows of the data frame one at a time and do something else, maybe that's not the best way. I've seen pandas read CSV a lot. It's a really nice function. It just works until that really big file is bigger than your machine can handle, and then you have to start doing not so fun things. Generally, everything is a pain when you start running into memory pressure, and you have to work around it. And there are lots of ways to work around it, but why go to the effort if you don't have to? So in this first example I have for this, first one reads everything into a data frame, then does some arbitrary function to all the rows in the data frame. It's nice, it's simple, it's understandable. But suddenly we have everything in memory and maybe we don't need it there. In the second example, we're just going to go through the file line by line. We're going to load a line by memory, do the processing on that line, move on to the next thing. We don't need the whole file in memory. That file can be as big as we like. We're limited by hard drive space, not by memory space in the second line. And the implicit magic here is that for line in F is a generator. It's not loading all of the data into memory. It's just going to go through one line at a time. We can make that a bit more explicit with list and generate by comparing list and generator comprehensions. So in the first case, if we try to do something to every line in the file, it's going to do all of that computation in one hit. It's going to store everything in a single, potentially giant list in memory before it moves on to the next step. On the second line, all I've done is replace the list comprehension with a generator comprehension. Do something is not evaluated until later on. The nice thing about generators is that you can compose them. So you can feed the result of one generator into another generator into another generator. So suddenly what looks like some funky processing can just become a stream, and a lazily evaluated stream at that. So for this problem, we only need to worry about the memory of one line at a time, not the amount of memory we need to hold the whole result set. So taking a break from Python itself and looking a little bit broader, maybe you shouldn't be trying to do that in Python. Maybe you're making your life harder by not using all the other infrastructure you have available. Maybe putting your data in a database is a good idea. The nice thing about databases is that generally, all of the hard operational problems like, is the data backed up? How do I back it up? How do I replicate it? Is the data's integrity still, does the data still have the required integrity? Does every Are all the constraints that should be on this data still valid? It's a solved problem. You don't need to think about it. I wish I had learned databases and SQL a lot earlier, because I realized when I learned it that I'd re-implemented joins like 3 times in 3 different contexts, and I didn't need to. That was cool and sad all at the same time. Also, SQLite is in the Python standard library, so you can't say you don't have a database. I think the single biggest thing that SQLite does is that it still has durable transactions, so you can rely on it to keep your data once you've committed that transaction, and you don't have to worry about partial states. A lot of the time, the hard part about long-running computations is being able to resume them and having save states and resume points, so you don't have to worry about your 3-week-long computation dying in the middle. SQLite just gives you the nice transactional guarantees for free. Plus, personally, I think SQL is a very productive language for a specific subset of data problems. So I would much rather use SQL than pandas. I'm sorry. Please don't hold that against me. On top of that, there are a lot of databases out there. There are a lot of domain-specific databases. There are a lot of domain-specific extensions for databases. So if you can push some of the hard problem onto something else in your stack, maybe you should consider that. Maybe you don't need to solve everything in memory in NumPy land. So if you've got a graph or a network problem, you could put it in Neo4j, for example. Full text search, either your relational database or Elasticsearch. GIS, maybe you want Postgres plus PostGIS. I think that's how you pronounce it. I've already said I like relational models. You can probably figure that out, so I won't overthink that one. Lastly, I think that analytical databases like MongoDB and ClickHouse and the hosted alternatives like BigQuery and Redshift and the other AWS one whose name I can't remember right now are a really, really nice complement to the numerical Python stack. Because if you've got it in a database, you can separate the concerns a lot. And then your numerical Python stuff maybe only needs to worry about a subset of the data or a subset of the problem. And you can simplify your life by only pulling out what you need instead of pulling in everything. Another recommendation I want to make, or another suggestion, is that maybe you should have a quick look to see if there's a smaller task-specific library. If your domain happens to fit in integer bit sets, you probably want to be using roaring bitmaps anyway. There are actually like 3 or 4 different wrappers for the C library. You will probably not build software that is better than that. You will not build anything faster than that. I think this is as close as it gets to CPU, to making the most of modern CPUs. So if you happen to have a bit set problem, you want to use that. There's also a sorted container library which has lots of interesting data structures in there with different kinds of sorting for different kinds of problems. So maybe that can make your life easier just by using that instead of pulling in the big guns. I guess to kind of wrap up, and I realize I put those in the wrong order. I think the first wrapping up point should be don't be afraid to mix and match. You're not constrained to solve everything in NumPy or SciPy or scikit-learn. You can bring in the rest of Python too, because you've already got a big chunk of it. The standard library is very good. The base data structures are very good. Don't force yourself into just the numerical domain. You can use other stuff too. You're allowed. And I guess the other thing is that I don't think, when you've made the decision, you've evaluated your problem, and you've gone, yeah, this is actually a numerical problem. This is, it's going to take me so much longer to do it any other way. If you're doing that, go for it. Go deep. Even NumPy, as the base of the library, has so many cool functions. Just write the documentation when you find the cool one. Also, just if somebody wants to explain the Einstein summation stuff in NumPy, I would really like that because I have tried and failed a few times, and I could use some help. Thank you.
Thank you, Sam. Do we have any questions? We've got about 5 minutes left for questions. Okay, I got a question to start then. So part of your talk was saying that you don't need to go straight into NumPy, pandas, etc. You can just use the base libraries. But at least in my personal experience, like I started off Python that way, going deep into base libraries, and I did way too much terrible stuff with them. How do you help a beginner have that knowledge when to transition to something fancier?
So I was going to say it depends, but that's really not a useful. I think one part is the background, like is this a beginner software developer? Is this a beginner data scientist? Is this a PhD student working in a particular problem domain for a particular purpose? And I think the answers for all of those people are different. And to be honest, I think it's one of those things where you're going to be wrong half the time anyway. So I think it's worthwhile to go. Maybe the advice would be trust your gut after evaluating the options. Remembering that the options for there is probably the main point I want you to take away, is that there is the option to not use this. Not saying you shouldn't use it, because you probably do want to use it in lots of cases, but if you remember that there are other options, there are other things out there, there are other Python communities, idioms, packages, and so on, I would definitely trust your gut after thinking about the other options. Which again is not very useful advice, but you asked the hard question first. So.
That's true.
Hello, yeah. So you mentioned like lists and dictionaries and things like that. So I guess a really long dictionary could be like a pandas series. Is going through either of those, like a massive one, for example, which is more efficient on the large scale? On the large scale, people always say that pandas and NumPy is like super efficient, and then the other stuff like lists, for example, would be not so efficient.
It depends a lot on the exact problem. Like if you're just looking up a single thing in a single dictionary, it's probably not actually worth benchmarking. If you're doing lots of lookups, you probably, that's a really, I think because the problem with with doing that kind of comparison is that it's very, very task specific, what is the most appropriate. And also, I think if you're at the point where you're doing that kind of benchmarking, you always need to tie it back to what is the actual problem I'm solving? Does it matter if this takes 5 microseconds instead of 1 microsecond? Maybe it doesn't. If you're doing that lookup trillions of times, then it really does matter. And I'd probably say that the better answer there is to figure out what's the actual problem and the objective of that first before you worry about tech choices like.
Okay, cool, thanks.
Track.
Hi, nice talk. I really liked it. But you talked about loading big files and using generators. On the other hand, there is a memory map function that doesn't load the file at once.
Yes.
Do you have any insight? Is there any difference in speed between making generators and loading files with memory map functions? Any significant difference?
I couldn't comment on significant differences. I would say that there's a pretty big conceptual difference in that when you're talking about memory mapping things, suddenly you're working around a limitation of your machine rather than there's a conceptual overhead to even formulating your problem in that way, which maybe you don't even have to think about with the generators. Because I think sometimes the real constraint is programmer time and the amount of time you have to write documentations and pass that knowledge on to your team rather than how long this is. I mean, there are probably some cases where you have to memory map because a generator is going to be too slow, if that also answers your question.
Thanks, Sam, for a wonderful talk. I just had a question regarding NumPy, that I find it much easier to do element-wise comparisons, like element-wise operations, when I'm dealing with building masks and multiple masks to filter out my data. And I just find functions like NP, logical and logical OR quite a lot easier. Do you have anything else, any alternatives, or is that really the way to go?
It sounds like that's the right solution for your problem. Within the base data structures, I don't think there's anything quite the same. Maybe list comprehensions or generator comprehensions. But yeah, I mean, it also sounds like you know what your problem is, and it sounds like it's a really, really good fit for a numerical domain, so you probably don't need to look too hard at other options, which is good. I think there was one more question, if we've got time.
No, unfortunately we're out of time now, but I'm sure you can find Sam in the morning tea break, which is what's happening now. And just as a small appreciation for giving a talk.
Thank you.